Recording is rolling. Welcome to Tuesday, October 26th. So we're going to finish this chapter 11 puzzles. I think there were just a couple of questions left there. Then, do you guys remember this conservation of energy table? 3 pages. We did most of them, but there were a couple of rows left, so let's go tidy that up. Then, there is a new poster, well, as of the weekend, that looks, where'd it go? Oh, here it is. Okay. Looks like this right here, that involves a block compressed against a spring, goes pew, and then it's shot through this loop. And this is actually one of your quiz questions. You guys see, here, you guys remember this open notes take-home quiz? Looks like number 7. Number 7 looks exactly like that, doesn't it? So I'll take you guys through that one. There's a related question that involves the minimum height of a roller coaster to make sure that it goes through a loop that's not too far off from that one. So talk about that. And that goes pretty close to the class. So yeah, just do a bunch of little conservation of energy stuff right here. Conservation of energy. Right, so chapter 11 puzzles. We've done all the chapter 10 ones and then chapter 11, and I think we're on these last couple right here. So, number 81, Hakeem throws a 10-gram ball straight down from a height of 2 meters. The ball strikes the floor at a speed of 7.5 meters per second. What's the initial speed of the ball? All right, now, I'll do what I normally do is I'm going to change the numbers a little bit. But before I get going on that, right, if you throw a ball straight down from 2 meters and it strikes the floor that fast, right, well, what if I change this premise a little bit? What if instead of throwing the ball down, which that's the question is how fast do you throw the ball? What if you just dropped the ball instead? I wonder how fast it would be going after falling for 2 meters. Okay. Do you think you can figure that out? That's a different question. That's not what's being asked. But wouldn't that actually be just the Galileo question? Hey, Galileo dropped the ball from some height, didn't he? Okay. And we've been doing this, so this has been our framework for solving problems this week, is that energy is conserved within a closed system. So energy at the top is potential energy at the bottom is kinetic energy, so this form and this form, and they have to equate because energy is conserved. And then you can solve for stuff. So if you solve for the speed at the bottom, it's square root 2gh. You guys remember all that? So what if that height was 2 meters? What if it was 2 meters, just like your textbook? I wonder what the speed would be if you just dropped it. Say it starts from rest. It'd be square root of 2 times g would be 10 meters per second squared times the height drop of 2 meters. That would be 6.3 something meters per second. But your book says 7.5 meters per second. Okay, so he had to have thrown it. So it's sort of a side thought there, but there is like a minimum value of that number. So number 81. Notice in that full explanation data, I said nothing about the mass of the ball. Right? Even though they gave you the mass of the ball, you guys know it's probably going to cancel out. So what if you have, say, a ball that you throw straight down at some speed? Call this B naught. Okay. Got a ball, some mass, whatever. Okay. And then, so it's going down kind of slowly. Okay. And then at the bottom, say at the floor, now it's picked up to a really fast speed, moving really fast. Call it V final. Okay. And there's a height change from there to there. There's some height change. Call it H. Okay. So let's do that conservation of energy setup. So the sum of energy at the top, say initial, equals the sum of energy at the bottom, at final. Okay. So closed system. Now this is a closed system of the ball and the earth, right? Because the earth and ball have a gravitational force that's what's causing it to speed up. Now at the top, there's actually 2 different kinds of energy. What are the 2 different kinds of energy? What and what? Potential and kinetic. Yeah, potential because it's elevated height, and kinetic because it's throwing it. So I'll go mgh plus 1/2 mv squared. Okay. And this is v naught because it's at the top. Okay. Down here, what kind of energy? It's all kinetic. Okay? It's all 1/2 mv squared, and this would be v final. Is that true? Because the height's defined as 0 at that point, so potential energy's gone. Right? You guys notice if you took away the throwing, this would just turn into the Galileo problem, right? Right. So I'm going to make up my own numbers, but I'm not even going to make up a mass of the ball because you guys see all these three terms, the mass just cancels out anyway. Okay. So just, it doesn't matter what the mass of the ball is. But what if, I'm going to call height 3 meters. So here's where I'm making up my own numbers. Okay. And I do a side thought here because I want to know what is the minimum speed that I have to make up for v final. So what is square root 2 times g times h? 7.74 something. Okay, so v final has to be at least 7.7 something. Right? If it's less than that, then there would be no solution. This wouldn't even make sense. So I'm gonna call this, I don't know, 9 meters per second. Okay, so I'm in the clear there, just barely, but that'll work. And then your book just told you some numbers. Right, so now let's just start feeding the numbers. So we've got a gravity field of 10 meters per second squared. I've got a height change of 3 meters. Now we don't know the throwing speed, that's the question. But we know that this thing is crash landing at, say, 9 meters per second. And don't forget to square that speed. Are we sure? Okay. All right. So we've got, let's see, 30 meters squared per second squared plus 1/2 v naught. Oh, whoops, I forgot squared. 1/2 v naught squared. Right. Equals, so what's it come out to do? 9 squared is 81. 81 divided by 2. 81 on 2. That's 40.5. Meters squared per second squared. Like that. Right. Okay, so then see, subtract this over. So minus 30, look at that. 1/2 v naught squared is 10.5 meters squared per second squared. Okay. Multiply both sides by 2. 21 meters squared per second squared. And then finally take the square root. Now, meters squared per second squared, that's like some weird abstract unit. But then when you square root it to finally get the speed, now it just turns back into meters per second, which makes sense. So the throwing speed for my case would be 4.58 meters per second. Okay. Guys good? All right. While you guys are finishing that one, digesting that, let me do a side note here. You guys remember the old way of doing this was final velocity squared equals initial velocity squared plus 2ax. Right? That's a real old kinematic formula in this class. So I want to test this and see if this all works out. So I'm going to plug in my answer and see if it, well, tells us this is 9 meters per second. I'm about to find out. So this would be 4.58 meters per second. I square that. Plus 2 times 10 meters per second squared is the rate it's picking up speed. And it does that over a height change of 3 meters. Okay. I wonder what all this is equal to. So 4.58 squared plus 2 by 10 by 3. That is exactly 81. And when you take the square root of that, you get 9, which is the final speed. So 9 meters per second squared does equal that. Check. And we're good. You guys good? All right. And we have one problem left for chapter 11. That's number 84. Oh, I like this problem a lot. Also, the one we're about to do, I think I turned to a quiz question too. Yeah, I did. You guys see number 8 on your open notes take-home quiz, number 8? You guys see this guy swinging on a vine? Or swinging on a rope? That's pretty much exactly what we're doing right now. Suppose a chimpanzee swings through the jungle on vines. If it swings from a tree on a vine that's this long, like so many meters long, at a starting angle of so many degrees from the vertical, what is the chip's velocity when it reaches the ground? Let's say the ground is like the lowest point in the swing. Okay. How fast is it going to be going? So number 84. So let's get a big old vine going. Like this. Right. Get this guy swinging on this thing. Okay, so from there to there, they told you the length. So I'm gonna make up my own length. Let's see. That many meters. I'll go 11 meters. 11 meter long vine. Okay. And they also told you the starting angle from the vertical, theta. So I'm gonna call it, let's call it 29 degrees, like that. I wonder if this guy starts from rest, right, which they didn't have to do. They could have said he like kicks off, so he has initial speed, but if he starts from rest, just drops down, so a little bit simpler. I wonder how fast he's gonna be moving at the bottom. So if his V naught is 0 meters per second, what is VF? That's what we're solving for. Good for that. And if you know the gravity field is about 10 meters per second squared, then there's enough information there where you could solve this. Notice they did not give you the mass of the chip, but that would cancel out anyway. You guys could you've probably seen enough of these so you could guess what's going to happen. We're just going from potential energy to kinetic energy. So height equals zeros at that one. All right, so this is eventually going to feed into the framework. Sum of energy at the top is equal to sum of energy at the bottom. That's true, right? Okay. At the top, it's all what kind of energy? Yeah, potential energy. MGH. Right. Well, let me pause there, because what refers to what? Like M is the mass of the guy or the chimp. G is the gravity field. Do you guys see what the height change is going to be? You guys see on the picture, it's going to be however much he's elevated is this value right here, call that H. Is that true? Okay. This is about to turn into a geometry problem, because how are we going to get H? Let's finish this off and then figure out how we're going to get that. Okay. So at the bottom, it's what kind of energy? Yeah, kinetic 1/2 mv squared. Okay. In fact, you know what? When we eventually solve for this V, how many of you guys think that V is just going to end up being square root 2gh? Okay, because that's exactly the form, isn't it? Okay, so it's kind of backwards, but it's the same thing. Okay. So it will be that. But all right, if only we could figure out what that H is. So this is really a geometry check problem. How can you guys figure out what H is? How about this? And guess his length L. And I think I gave this as a hint on the quiz. Isn't that the same thing as this length? I mean, if this is 11 meters, isn't that 11 meters? 11 meters, right? Okay. So if you could somehow figure out what this distance is, could you just take the full 11 meters and subtract this off? And that would leave you with that height change, right? Is that true? Okay. And okay, so how could you get this? Doesn't this look like a right triangle? What do you guys see that right triangle right there? You see that? Right. This is some of the first stuff that I quizzed you guys on was, can you work your way around a triangle? Because triangles just keep coming back in this class. So who can tell me what this segment is equal to, since you guys know trigonometry? It's equal to what times what? 11 meters multiplied by cosine of 29 degrees. Exactly. Yeah, so this is 11 meters multiplied by cosine of 29 degrees. Let's get a number for that. So what is 11 cosine 29 degrees? That is 9.62 meters. Okay. Well, if that's 9.62 meters, and this full length is 11 meters, which of course is just the same line, okay. Then isn't this height 11 meters minus 9.62 meters? So what's 11 minus that? Okay. I'm looking at 1.38 meters. Okay. That's your height. Well, that's a height change from point A to point B. Okay? 1.38 meters. Right, that's going to feed in right here. Right there. All right, so let's let's continue this adventure. Ooh, looks like the mass cancels out right here. You guys could predicted that. So I've got gravity field of 10 meters per second squared across a height change of 1.38 meters is equal to 1/2 v final squared. And that you guys can solve, right? Cross multiply the 2, take the square root. Well, yeah, v final is, see, it's a big old square root. I've got, oh, hey, it's the square root 2gh. Just like we were thinking a moment ago that should be, right? There's 2, there's g, there's h. Just like the Galileo problem. Yeah, square root 2gh. With the extra geometry problem thrown in the mix. So square root of 2 times 10 times 1.38. I'm looking at 5.25 meters per second. You guys get there? Let's go to this energy table. So we were doing these last week. We did most of this table, and then there were just a couple left. So just for completion, but I did give you guys points in the grade book for this already. You may have seen this, so I'm not actually going to take this up, but if you're curious to know, how do these last two work out? So remember I gave you a bunch of scenarios. We're saying what's in the closed system. Now there were a couple of open systems. These are going to be closed. Okay. And then can you solve for like the speed of the final point using conservation of energy? So this scenario has a ball rolling down this incline without sliding. So ball rolls without sliding down the length L. Now, give you guys some other details about this one. This is going to sort of draw on future content a little bit, but talk about it too. So I will tell you guys, if this was frictionless, like an air hockey table, the ball would not roll at all. It would just go down. Yeah. Would look kind of weird, but that's what it would do. Right? You do need friction to get it going, but this is static friction, not kinetic friction. And what that means is that there's no work that's being done on the system. And the system, I'm talking about the ball, the hill, and the earth. Right? There's, or maybe just the ball and the earth are the important ones, right? So, yeah, the number of joules will equate, and you can treat this as a closed system. So the energy of point A, well, that looks like mgh, doesn't it? Just the ball sitting on top of the hill. Maybe it's at rest, or something like that. I wonder how fast it's going to pick up to by the time it gets to the bottom of the hill. So, like, what's the energy at point B? Okay. Well, we're going to call this like a mix of energies. So some of the energy is going to go into kinetic energy, but I'm going to specifically call this translational kinetic energy, 1/2 mv squared. Right. Then say plus, because there's another part. There's another place where the energy is also diverted into. Right. Right. So here's where the future content comes in. Do you guys think that different balls would roll down differently? Like, for example, what if you had a bowling ball, which is kind of solid all the way through, versus a basketball where all its mass was pretty much on the surface? Do you think those two balls would roll down differently, and there would be different speeds and different times to get to the bottom? There would be. Right. So that's related to a concept that we'll get into probably in late November, December, that called rotational inertia. You guys remember I gave you this quarter page a while back? Right. So some of the stuff we've worked with, like the kinematic stuff, like V is omega, well, linear speed V is analogous to omega angular velocity, like how fast it's spinning, for example, right? But we didn't get down to this bottom stuff, right? And now we're going to start touching on it, so just plant some ideas that's going to come back in the future. So mass has represented two things in this class so far. One thing, more recently, it's like gravitational mass. So there's some gravitational attraction between masses. Right? But before that, mass represented inertia. So if you push on something with a force, the more massive it is, the less it wants to accelerate, right? Because inertia. What's the sort of rotational equivalent of that? Say like a basketball versus a bowling ball. Because if you try to spin a basketball and you try to spin a bowling ball, they actually respond differently to a force of the surface causing that spin. So this is called moment of inertia. And it's a sum of mr squared So it's like if you add up all the little mass times radial distance from the center, square. Okay, so if you add up all the little bits, then what's it come out to? This is a table of values we'll look at in the future that's different for different shapes, but for now, just know this. It's 1/2 I omega squared. See how that looks like 1/2 mv squared? It's analogous to that. Okay, so the energy in the system, which started off as potential energy, actually gets diverted into two things. It's translational kinetic plus rotational kinetic. But one more step we can go with this though is this v linear speed, which you get like by pointing a radar gun at v at the ball point v, and this omega, which is angular velocity, which is like spin rate. Those are related to each other. Now, you guys know this too. This is something you guys have already learned. So just to remind you guys, see a couple Roosevelts here. Give us a spin. Don't these both have the same angular velocity, like same hertz per time? Right. But they have wildly different linear velocities. Right. So the one that's further out, it has a faster like radar gun speed, faster linear velocity, and those are related to each other. You guys might remember this because v is equal to omega times r. So if this one's about 5 centimeters out, this one's about 10 centimeters out from the center point, central point. If you know the spin rate, which is the same for both, okay, you multiply by that radial distance, you'll get the linear speed. Okay, and vice versa, you can also divide by r and go backwards the other way. Okay. So get some paper here. Okay. Here's where we're going with this. Sum of energy at the top is equal to sum of energy at the bottom. Okay. The original MGH is going to turn into 1/2 mv squared, but also plus 1/2 I omega squared, okay? Where that omega is the same thing as v divided by r, where r represents the radial size of the ball. Okay? So once you sub that in, MGH 1/2 mv squared plus 1/2 I, it'll end up being v squared over r squared. What it turns into. Okay. This v squared I can factor out of these two terms. I have three terms, right? Point, point, point. You can factor this out. Okay. So MGH is, at the same time, I'm going to take this 2 and cross multiply it up just to get rid of that fraction. It'd be m plus I on r squared all times v squared, like that. And then if you want to solve for that v, because that's the question, what's the speed of point v? You see, I'm just going to take the bracket of this stuff, divide it down, and then take the square root. So v is going to be a big old square root. And have 2 mgh divided by bracketed stuff. Like that. So just copy and paste that over here. So the speed of point v is equal to a big old square root. Okay. 2 mgh over bracket m plus I on r squared. Okay. Notice this is not too far away from v square root 2gh. Okay? Pretty close to that, square root 2gh. Okay? And then we've got a mass value up here, but also something to do with mass down here. And then last one, 2 asteroids start from rest and gravitate toward each other, and they have the same mass, so mass m, mass m. Okay, start from rest. Now, what's in the closed system? I'm going to say each asteroid. Okay. If they start at rest, doesn't that mean that there's no kinetic energy to start with? Maybe later, but not yet. Okay. So there would be all potential energy, wouldn't there? But if we're talking about 2 asteroids, then as they get closer to each other, the gravity field is going to increase. So potential energy, I can't say mgh because that lowercase g changes. It increases as they get closer. I have to use the universal form, which is negative g m m on radial distance. And they'll do so sub a because that was the initial case, right? Going from point A to point B as they get closer together. Okay. So initially they were RA away from each other. Okay. Then by the time they get closer to each other at point B, well, there's still some potential energy, but not as much. Negative g m m on RB. Okay. Now the fact that RB is smaller because they're close together, that means you're dividing by a smaller number, which means this fraction is bigger. Bigger number? Wait, what? but it's negative. So maybe you're going from like negative 10 joules to negative 20 joules. That means there's an extra 10 joules somewhere around the system, and that's all what kind of energy? If they're going faster, 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 kinetic, that's energy motion, 1/2 mv squared. And I'm not going to solve this out with you guys, but you guys see you could just set this equal to this, like equate this box to this box, and then solve for v, just do some algebra. You could do that, right? Okay. So not picking up this table, just for you guys to see these different scenarios, but that's how you finish those. Spring and loop question. You guys ready for the spring and loop? All right. So this one right here, which is also number 7 on your take-home quiz. Take a look at that one. Okay, so here, we've got it all set up here. Okay. So we're pressing this block against the spring. Right, there's a bunch of energy stored in the spring. Right, that right there. Okay, then let go, pew, fly around the loop. Right. And then conservation of energy, you need some initial and final point. So let's say this point and this point. So the final point is the top of the loop. It could be. So that energy would have gone 2 places to get to that point. One thing it has to go into is lifting the block against gravity. So that's the height of this loop. Okay. And whatever's left over is going to go into its speed. Okay. And it better be in motion, because if it runs out of speed by the time it gets to the top, it's just going to fall off the track. Okay. So if you want to get all the way around, there's got to be some kinetic energy. Actually, the next question I've got for you guys is going to be related to like that question of like how much does that have. Right, so yeah, before we actually get solving with it. Oh yeah, before we get solve this with you guys, I've got a side question for you, which is, do you see how you'll see this too if you ever go to a theme park, you see a roller coaster ride that has a loop. Right? You guys see how this is kind of like a teardrop shape? You guys see that? It's not actually a circle. Now, a lot of times in this class, I know we made a lot of simplifying assumptions, like no air drag or something. One of the simplifying assumptions we usually make for roller coaster loops is that it goes right to a circle, right? And then the height would be equal to 2 times the radial size of the circle. But in reality, you don't actually see that. If you go to the theme park, you actually see like a teardrop shape. Right? And same thing here. This is called a spiral, right? Where, see, the radius of curvature at the top might actually be a circle that's only this big. The radius curvature, like down here, would actually be like part of a much larger circle, right? Now, question for you guys is why? Why don't you go from a straight track directly into a circle? Why is it there's this gradual like spiral shape into a teardrop? Why would you do that? You guys remember centripetal force? Okay. So if you went from a straight track into a circle, then you'd be like, okay, just inertia, just like you're driving along, no problem. And then you would like, bam, you just like this centripetal force would just like all of a sudden just hit you all at once. And that would be really jarring, wouldn't it? Okay. So yeah, so by having this gradual spiral shape, then you can avoid that. Same thing with traffic. If there are any roads that are curving around, you never want to, as a traffic engineer, have a straight road go directly into a loop, although sometimes we do that in this class just for simplification. But yeah. Ideally, you'd like to have like a spiral shape that gradually leads into it. Okay, but let's solve the problem related to this. So what if I gave you spring constant, the compression amount, the mass of the block, which doesn't cancel out in this case. The mass does matter. Okay? Anytime there's a spring, that's usually the case. The gravity field and the height of the loop. Would you be able to solve for the speed at the top if there's no friction? Could you guys do that? Okay. Let's run through an example. Let's say that, I'll do a setup. So sum of energy initial equals sum of energy final. Go 1/2 kx squared. That's the source of the energy. Okay. Goes into 2 places, lifting the block against gravity, and also whatever's left over goes into kinetic energy, motion. Okay. What if you're solving for this v and I give you a bunch of numbers? So what if I tell you the spring constant is like 1,000 newtons per meter. The compression amount is, let's say, 10 centimeters, so that'd be 0.10 meters. All right. Let me make sure. Because if I'm just making up numbers off the cuff, I got to make sure that it's going to work out okay. let's say the mass of the block is, here. Sorry. So here, okay. This mass block is, let's say it's this guy right here, just 100 grams. Okay. 100 grams, if you plug that into this equation, you can't say 100, you have to say what? Okay, 0.1 kilograms. Would that be true? Okay. And gravity field is about 10 meters per second squared. Okay. Okay. Let's say the height change is like 3 meters. Okay. And then mass shows up here again. Remember the mass was 0.1 kilograms. Okay. I wonder what the speed at the top of that loop would be. Okay. So you know the spring constant, you know how much it was compressed, you know the mass of the block, which shows up a couple places, you know the gravity field, you know the height change. Okay. How much speed would be at that point? Okay. So let's see, we've got energy counting, right? This number of joules equals this number of joules plus this number of joules. How many joules did we start with? Well, what is 1/2 times 1,000 times 0.1 squared? I'm looking at 5 joules. This is 5 joules of energy to go around. 5 joules. So that 5 joules, where did it go? Well, some of it went into lifting block. 0.1 times 10 times 3, that is 3 joules to lift it. Okay. That must mean that there are 2 joules left over to go into the speed. Right? So that's 0.05 times v squared. But if you like thinking of it that way, you could say, well, that has to be 2 joules. Actually, that's the next algebra step anyway, isn't it? Okay. It's just to subtract 3 joules over. So 2 joules of energy are 0.05 kilograms times v squared. Okay. So do some algebra, divide both sides by 0.05 kilograms. So divide 0.05 kg, 0.05 kg. Okay, so 2 divided by 0.05. Okay, that's looking like 40. And then joules divided by kilograms, that's meters squared per second squared. If you follow through the units, that'd be v squared. Okay. So last step, take the square root of both sides. What's the square root of 40? I'm looking at 6.32. And then, oh, hey, meters squared per second squared. The square root of that is just meters per second, which describes the speed. Yeah, so all good. Worked out. You guys good there? You guys be able to do that quiz question? All right, so next question I got lined up is not too far from that one, but let me switch my screen over for a moment and play a quick video for you guys. Okay. Mute that. Okay. Have I shown you guys this before? Okay, wasn't sure if I did. All right, there's a bowling ball at the top of this track, and release that bowling ball. And oh, look at that! It goes around that loop, and that guy wearing the helmet, hey, he's all right. Right? Now, would the bowling ball be most vulnerable to fall off the track? Let's see, right at the top. Like right there, right? What if the speed of the bowling ball at that point was 0? Would it just fall off the track, like crash against the guy's helmet right there? So it better have some speed to get around. That sounds kind of similar to the problem we just set up and looked at, except there's no spring involved, right? But there's a height that it fell from originally. Is that true? So that's what I want to do next here. Is let me draw pretty much what you guys saw. Right. What if you were what if you had this roller coaster? Okay. I'm going to have this roller coaster go through. I'm going to do exactly what I told you guys not to do if you ever design a roller coaster, which have a straight track go into a perfect circle, something like that. Okay. But, just a simplification for what we're doing. Okay. Right. And what if there's no engine on this coaster to provide extra force? So it's just going to get around based on its own to just let potential energy go to kinetic energy sort of thing. Okay. This starts at some height h. That's going to be the question: is what is the minimum height to make sure that this roller coaster gets around this loop? And something else you have to know the radial size of this thing. So I'll call that r. Maybe I'll give you guys a radial size of like 10 meters. 10 meters. Okay. What would what's the height you have to drop from to make sure that it gets around there? So here's ground level that we're measuring with respect to. Here's the height when it's at that critical point, and it better be in motion. And that's part of the question, is figure out, well, how fast does it have to go, with respect to like some variables. Okay. And then, okay, what's the drop height? You guys see if you dropped it from the exact same height, that even if there's no frictional losses, it's just going to have to go to 0 speed and fall off the track. So it can't be the same height. It's got to be higher than that. But like, how much higher? Okay. Let's look at a free body diagram at this point. Let's use Ready for this free body diagram. Okay. There's usually two forces on this coaster at this point. Let's say it's getting around with sufficient speed, Wouldn't there be a weight and also a normal force acting down? So its weight would be acting down. There would also be a normal force from the track pushing down. Right? But what if it's not sufficient speed? What if it just barely gets around? Right? Like it's on this curved path, but the only force acting as a centripetal force is just the weight. Maybe the normal force approaches 0. Okay. That would actually be the critical point that we'd be interested in, would allow you to find minimum height. So we're going to start there. I'm going to say that the centripetal force, which is usually weight plus normal force. Okay. Well, I'm going to let that normal force go to 0. So let this guy go to 0 newtons. Okay. And just be provided only by the weight. Centripetal force, you guys have a formula for that. It goes mv squared on r. You guys remember that? mv squared on r. Okay. And the weight, well, that's just mg. Okay. The normal force just went to 0 at this critical situation, right? Okay so far? Okay. Now, what's going to cancel? Like mass. Probably not a huge surprise there. Okay. Do one more thing here. Cross multiply the r. V squared is equal to gr. Okay. So the minimum speed would be the square root of gr. But actually, I'm going to pause right there. You guys will see why in a minute. I'm going to eventually substitute this expression into a conservation of energy setup. So what does the conservation of energy setup look like? Oh, you know how it's going to start. Sum of energy initial is equal to sum of energy final. Okay. And initially, hey, isn't it all potential energy right here? So doesn't that go mgh? Okay. That's like the source of energy. Okay. We're eventually solving for what is this h? Okay. And what is the final energy? Well, the final energy over here, it's actually an energy mix. Okay. If you count h0 meters to be this bottom line down here, because doesn't the coaster have to go up this height? And what is this height in terms of the radius of the circle? I see it's going to be 2r, which is like 20 meters. Okay. So in terms of variables, let's see, mg times the height of 2r. Right? So here's the source of energy. Okay. Some of it was diverted into rolling it back up to this level. Okay. But there's going to have to be some energy left over to go into 1/2 mv squared. Okay. So this number of joules equals this number of joules plus this number of joules. And here's where that substitution comes in. So see that v squared equals gr. Okay. That's going to go right there. Is that okay? From all the centripetal force stuff from a couple weeks back. So mgh minimum goes to 2 mgr plus 1/2 mgr. Is it? Hey, I have 3 terms, and they all have what in common? M and G. Okay. So the fact that mass cancels out, probably not a huge surprise, means that it doesn't matter if it's an empty cart or if it's full of passengers. It makes no difference to the solution. Okay. And the fact that G cancels out means that whatever the solution is, You could take this to the moon and it would be the exact same solution, right? H equals, I see 2r, I see another half r, that's 2.5 times the radial size. You could also call that 5 halves times the radial size if you like fractions. Okay. And then, I did give you guys a number. So if the radial size is 10 meters, you guys see that would just be 25 meters? Because 10 meters times 2.5, it would be 25 meters. Want an exact like number solution. Guys okay? All right. Let's flip over and just play a video demo to end this class. Got it.